And we were into really sort of covalent bonding and sort of talking about the different types of bonding. And there's really sort of three different categories of bonding that we talked about. Again, there's ionic bonding, which once again is always our metal and non-metal together. And because of those periodic trends, we again will see that transfer of electrons from the metal to the non-metal, again making our ions, cation and anion, which again, no sharing of electrons happening in that situation. On the other end of the stream, we have a non-polar covalent bond, or just a non-polar bond is usually called. And that is between two nonmetals. And because they do have similar sort of characteristics in terms of their periodic trends, we will get equal sharing of electrons. Like we saw F2 or H2 as well. And in the middle is a polar covalent bond, or just referred to as a polar bond, also between two nonmetals. And here we have unequal sharing of electrons. And again, the result of that unequal sharing of electrons is we do create this polar bond, which essentially means that there's a side to that bond where it is more positive and a side that's more negative. And we could draw this bond dipole arrow that always points to the more negative side of the bond, and the back end to the more positive side of the bond. Here, the fluorine takes on a partially negative charge and a partially positive charge there for the hydrogen. As we talked about, they are partial positive and partial negative charges because there is still some aspect of sharing happening with those electrons. So we have not got a full transfer of electrons like we see in an ionic compound, where we do get a kind of full positive and full negative charge that occurs. What helps us understand whether or not, for example, a bond between two atoms will be sort of polar or non-polar, I guess ionic as well. The big one that we look at is electronegativity, and we look at really the change in electronegativity values. And as we saw on that chart, basically the values run from 0 to 4. And we could take the difference between the electronegativity values of both of the elements within the bond, and that will give us what is sometimes referred to as the bond polarity, where again we could draw an arrow pointing in a sense where we do have a polar bond that occurs. Anywhere that is 0 to 0.4 is considered non-polar bond and considered equal sharing of electrons, which again means that there really is not going to be a positive side or negative side to that bond, kind of like a neutral bond if you want to think about it that way. As we talked about, kind of above 0.4, which I guess would be 0.5, to below 2 is some type of polar bond. And again, that would mean that we would still have sharing of electrons, but it would be unequal sharing, where we would have one side more positive, negative. And that's really where we would draw those individual bond dipole arrows to indicate that. As we talked about, above 2 is typically ionic, but it does not always in every ionic situation. And as we mentioned towards the end as well, you don't really need the numbers to figure out ionic, as it should always be a metal and non-metal, and it's a pretty safe bet if that's the case. You have an ionic bond happening. We also talked about the idea that, you don't necessarily always need the values. You can use the general trend in electronegativity to help you make a pretty educated guess as to whether or not a bond would be polar or non-polar. Again, if you're comparing something that's in the same row, probably going to result in a polar bond, with the one being further to the right being more electronegative. If you're comparing something in the same group, same deal, probably going to result in a polar bond if there are two nonmetals coming together. And again, the one further up would be more electronegative. So definitely if they're in the same group or in the same row or period, you definitely can make a pretty good guess. We also saw when we looked at those values that there is sort of a diagonal sort of relationship, not directly diagonal, but kind of down and over one sort of relationship, where you can get two elements that are different, but still share the same electronegativity values, like carbon and sulfur, for example, which would give you a value of 0, and it would be considered a nonpolar bond. So, those are a couple of things towards the right there, upper right of the periodic table, that you just have to watch out for to make sure you don't come across any of that. The last thing that we talked about, I think last time, was the idea that, typically speaking, bond polarity and using the change in electronegativity values is typically used really for bond polarity, which means all we're really trying to determine is between these two atoms how the electrons are going to be shared, is really what we typically use the change in electronegativity values for. The only place, as we talked about, where both the bond polarity and the molecular polarity will actually be the same is in like these couple of examples here, these diatomic molecules. And that's because they basically only have one bond in the entire molecule, which means if you can determine that the bond is nonpolar, then the entire molecule has to be nonpolar in that case, which means overall the molecule should be sharing the electrons equally. And if you can determine that the one bond there is polar in that diatomic molecule, then by default, it will also have to be a polar molecule for the same reason. As we'll talk about in the next chapter, again, when we get 3 or more atoms involved in a molecule, there's a couple different things that you have to look at to determine whether or not a molecule as a whole is polar or nonpolar. Yeah. So we're talking about in this case, really any two atoms. It can be those diatomic molecules, which are elements, which will usually always give you a nonpolar bond and a nonpolar molecule. But like HF, for example, is still considered a diatomic molecule. Diatomic molecule basically just means that there's two atoms, and they can be two atoms of the same element, or they could be two atoms that are different. Just like triatomic would mean there's 3 atoms basically, and termatomic would be 4. So in this case, it would apply to any molecule that is basically just 2 atoms. And it's really because of the fact that it just has one bond. So that's the entire molecule is basically made up of that one bond. So it makes it really easy to determine both bond polarity and molecular polarity. Other questions? Okay. Let's zoom in case we missed it. All right, there we go. We'll try it again. So here's again our sort of cutoffs that we did talk about. Again, up to 0.4 is considered nonpolar. Basically less than 2 is polar, above that, and again, in most cases, above 2. Another sort of classification that people don't use too much anymore, but sometimes people talk about bonds as being percent ionic character. And if something has 100% ionic character, then clearly it's more of an ionic bond. And if something has more of a 0% ionic character, then you have more of a kind of pure covalent bond sharing of electrons that occur. Not too much these days. People talk percent ionic character. They mostly talk in terms of polar bond, non-polar bond, or ionic bond is usually how they sort of break it up. All right. So as we saw, atoms with widely different electronegativities will form a ionic bond, and that's typically what we get when we kind of cross from one extreme of the periodic table to the other. Again, our metals and our nonmetals. And as we talked about, again, when we get the covalent bonding, the reason really we get that sharing of electrons is they're all sort of huddled there in the same spot on the periodic table, pretty much. And they all have very similar properties, which we've talked about, that they want to hang on to their electrons. They want to really gain electrons. So again, the best that they could compromise on is basically just sharing of electrons. All right, so we talked about this pretty much. All right, so what we're going to talk about now is actually drawing Lewis structures for covalent bonding, to show covalent bonding and molecular compounds where we have sharing of electrons. So earlier on, we talked about in this chapter how we use Lewis dot symbols or electron dot symbols to represent the formation of an ionic bond. We're going to talk here the steps that you really should follow when you're drawing Lewis structures for molecular compounds, which are guys that have covalent bonds and sharing of electrons. I would say that you should follow the steps here, and it will get you to in most cases, a pretty good structure that you should end up with. If you choose not to follow these instructions, you shouldn't do that. But if you choose not to follow these instructions, and you do it how I sometimes refer to it as kind of like piecework, where people will kind of draw each of the individual elements with their dots and then try to figure out how the dots come together to make the bonds and stuff like that. Usually what will happen in that situation is people will draw pictures that have not the right number of electrons, too many bonds and stuff like that. So when we draw Lewis structures for covalent compounds, we do want to kind of think about the electrons that we have to put in the picture as not necessarily belonging to a certain element. And sometimes when people do kind of piecework, they go like, well, nitrogen's got like 5, so it needs like 3, and this guy's got that, and it needs this. So it's best to think about the electrons as really how many electrons that we need to sort of put into our picture and sort of distribute properly between all the atoms. So the first thing that we want to do when we draw a Lewis structure is think about the skeletal structure of the compound. And this is really sort of the logical arrangement of how the atoms are put together. In a lot of cases, the stuff that we draw in this class, there's oftentimes like one guy in the middle that's the central atom, and then kind of like everybody else is attached to it. It is possible to have multiple central atoms and things attached to it. But a lot of times, if you have one element or one atom of one element and like 3 of another, then usually the one element's in the middle and everybody else is sort of attached to it in that sense. To help you decide what should kind of go into the middle, usually the one that is the least electronegative atom should occupy the center position. Hydrogen and fluorine will never occupy really the central position. They should usually be on the outside for basically 2 reasons. As we talked about, hydrogen should only have how many electrons? 2, which means it can never really be in the middle. Otherwise, it's going to have more than 2 electrons. So it's always got to be, again, on the outside, pretty much looking like that. It's pretty much what hydrogen should always look like. Fluorine should not usually be in the center either, because fluorine is the most electronegative atom you can have. So it will usually not find itself there in the middle. Once you sort of have the logical arrangement, probably the second thing here is really kind of the most important thing. We want to count up the total number of valence electrons that we need to do in our picture here. And we do need to take into account if we are drawing something that's a polyatomic ion, which has a charge, if it has a negative charge or if it has a positive charge, we do need to take into account the actual charge in our electron total. So if somebody has a negative charge, that means it has gained electrons, so we need to add that to it. And if something has a positive charge, that means they have lost electrons, so we need to remove that in terms of the count of electrons. Polyatomic ions, as we'll talk about, are ions, but they're actually held together through covalently bonds and stuff like that, sharing of electrons. So once you have the total number of valence electrons, which also another reminder, number of valence electrons can be found by looking at what on the periodic table? The group number, right? So number of valence electrons equals the group number. So once you have the total number of valence electrons, that number is important because when you're done with your picture, you got to hit exactly on the nose that number. You can't have any more, you can't have any less. It's got to be exactly to the nose on that number. Once again, we also want to kind of think about it, as I was mentioning, as sort of not necessarily these electrons belonging to individual elements, but as a whole, we got to kind of distribute these electrons sort of properly in our Lewis structure picture. Once you have the total number of valence electrons down, what you want to do is draw a single covalent bond from the central atom to each of the outside atoms. I personally will use lines for that. And again, if you want to use dots, you can, but I'll use lines to show the bonding atoms or electrons. Once you've drawn a single bond to all the outside atoms, you will have used up a certain number of electrons. what you want to do is take whatever electrons are left, should go on the outside atoms first, and they should go on as pairs of dots until each of the outside atoms have 8 electrons around them. Obviously, except for hydrogen, it should only have 2. Now, once you've filled up all the outside atoms with 8 electrons, if you still have electrons left, then they should go to the center atom, and they should also go on as dots. This is the part of the program where we do not double bond or triple bond right out of the box, just to make it more chemistry-like, yes. So again, don't double bond or triple bond. Start with single bonds, distribute all the electrons on the outside first, and then work your way in. At that point, once you start dropping some dots there on the central atom, you should be out of electrons, hopefully, at that point. So you should have placed all your electrons at that point. The last thing that you do want to check is to make sure that everybody meets the octet rule except for hydrogen, just again, only have 2. And it's at that point, if you see somebody does not really meet the octet rule, that is really where you want to try to fix it. And to try to fix it, that's where you want to lay up a double bond. And you really want to try to exhaust all your double bond possibilities, and hopefully that will fix it. And if it does not fix it at that point, then you should move on to a triple bond. So that's what you kind of should do in most cases to get yourself a pretty good Lewis structure that's drawn. You want to kind of save your double bond and triple bonds for a situation where somebody has not reached the octet rule to try to fix that. And again, you don't want to double bond or triple bond right out of the box. Any questions on that? Yeah. So let's take a look at one together to see how these steps should unfold. We're going to go with what is the Lewis structure here for nitrogen trifluoride. We're going to start with our valence electrons. So there's 5 for nitrogen. There are 3 fluorines, and each fluorine is group 7. So that's 21, and 5 is 26 valence electrons. So our picture, when we are done, should have a grand total of 26 valence electrons. When I look at nitrogen and fluorine here, besides the fact I only have 1 nitrogen and 3 fluorines, so nitrogen should end up in the middle because nitrogen and fluorine are in the same row, and fluorine is more electronegative and nitrogen is less electronegative. So we should put the least electronegative atom in the center. We'll just surround it there by some fluorines. And I put that last fluorine on the bottom, but you could put it on top. It really doesn't matter kind of where you put it. Once I have the arrangement, I'm going to do 1 single bond. And again, I'm going to use lines, but if you do want to use dots, you can, but I'm going to use lines to show the bonding electrons happening here. Each line, right, represents 2 electrons, which means at this point I have now placed 6 electrons up there. So we'll do a little subtraction there. I got 20 more electrons to go. Once again, they get placed on the outside atoms in pairs, so not singly. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have now filled up all the outside atoms with electrons. I have now placed on my picture a grand total of 24 electrons. I still have 2 more electrons that I need to place. Those 2 electrons will then go to the central atom there. And at that point, I have now placed a grand total of 26 electrons, which is what I'm looking for. The last thing we want to check to make sure, again, is that we have basically 8 electrons for everybody. So we got obviously 2, 4, 6, and 8. Each of these fluorines are identical, so 2, 4, 6, and 8. 2, 4, 6, and 8. And for our nitrogen there, obviously, we got 2, 4, 6, and 8. So everybody has 8 electrons around it. They've all met the octet rule. We have properly placed all 26 of our electrons there. Any questions on that? All right, so let's take a look. Maybe let me do this one. Let me do nitric acid here, HNO3. So if we want to draw nitric acid, we'll follow the same sort of rule. One of the first things you really want to do again is come up with the total number of valence electrons. So we have 1 valence electron for the hydrogen. We have 5 valence electrons for the nitrogen. We have 3 times 6 valence electrons for the oxygens that are there. That's 18, 19, 24, I hope. Yeah. So once again here, that number is really important because it is the total number of electrons that our picture should have. Now, nitric acid is a little bit different. There is a kind of slightly different arrangement. We definitely know that hydrogen should not be in the middle, right? And that leaves us between nitrogen and oxygen. And if we look on the periodic table, we have nitrogen, then oxygen, which means going in this direction. Oxygen is more electronegative, right, than nitrogen. So really, nitrogen should occupy a center position. And in this particular molecule, it actually has 2 center positions. So it has the nitrogen, and it has the 3 oxygens, and attached to one of the oxygens is actually a hydrogen. And if it was something like this that maybe you would not know how it would put together, I would probably tell you, but that's actually what makes it an acid there at the end there without hydrogen attached to the oxygen. So in this case, we actually have a couple of central atoms, and again, we definitely know that hydrogen cannot be there. So we're going to follow the same rules, even though there may be a couple more things there than we had on the previous one. So we're just going to lay up our single bond between everybody. So I'm going to single bond it there, I'm going to single bond it there, I'm going to single bond it there, and single bond it there. At that point, I have now laid up 4 lines, which represents 8 electrons. It's a lot of math. 16 we'll go with that we got left over at this point, I hope. So again, even though we still have multiple central atoms, which the nitrogen and the oxygen to the right here on my picture are both central atoms, we still follow the same approach. We're going to kind of work outside in, sort of distributing our electrons. So we'll start on the outside. Will I put dots on the hydrogen? I will not, because it is full, so we definitely don't want to do that. So we'll go to the other outside ones, which is the oxygen, and put them on. So that is 2, 4, 6, 8, 10, 12 at this point. The next outside atom is also the oxygen to the right, right? So we could still put some on there and do a little bit of that action there. So that's 2, 4, 6, 8, 10, 12, 14, 16 electrons. That's dots I put on there. At this point, I am out of electrons. I have now placed on there all 24 electrons. I now need to make sure that everybody is good in terms of the octet rule or the hydrogen rule. So hydrogen is good, right? This oxygen, 2, 4, 6, 8. Is good. This oxygen, 2, 4, 6, 8. So it's good. 2, 4, 6, 8 is good. And when we get to our nitrogen, it has 2, 4, and only 6. So it is not good. So in this case, the nitrogen is not good. So we do need to kind of fix it. And can I fix it by just laying up a couple of electrons there? I cannot, because now I have how many total electrons? 26, which is too many. So we cannot just, add a pair of electrons and hope for the best. Now, way we could fix this is to first try to make a double bond and see if that helps. I actually have 3 locations as to where I could lay up a double bond. I could double bond, here, I could double bond here, and I could double bond there. Because this is an acid, probably not going to lay up the double bond to the right there, but you could do it in any of those places, really. So if I want to make a double bond to fix this, can I just, draw a line? I cannot, because the same problem just happened. I now have 26 electrons, and that oxygen on the left now has 2, 4, 6, 8, 10 electrons, which seems like a little much in this situation. So when we do need to make a double bond, what we're actually going to be doing is we actually need to take a pair of electrons from an oxygen and actually bring them in to make the double bond. So I'm going to take these pair of electrons up here, and I'm going to bring them in to make the double bond. And obviously that would remove them from the oxygen and kind of put them between the oxygen and the nitrogen. And that would get me something that looks like this. All right, double bonded. That way. And now when I look at it, once again, my hydrogen here has 2 electrons. This oxygen now has 8 electrons around it. If we kind of go around and count, there are 2, 4, 6, and 8. The oxygen on the outside still has 2, 4, 6, 8. Oxygen on top, 2, 4, 6, and 8 with the double bond. And now with the double bond to the nitrogen has 2, 4, 6, and 8 electrons. So everybody has 8 electrons, which would make it happy. And this is the structure for nitric acid. Because we did have the option to have double bonded to the top or to the left, we could draw what is referred to as a resonance structure, where we actually just double bond there to the left instead of to the top. And we could have drew this structure as well. And a resonance structure happens because you do have more than one location as to where you can put the double bond. And those double bond electrons are what are referred to as being delocalized, which means, you know, at any given time, maybe they're at the oxygen on the left, maybe they're at the oxygen up on top, maybe they're at the oxygen to the right. And the true structure is probably somewhere between all those individual resonance structures that you could draw. But the simplest way to sort of draw resonance structures, go, where else can I make that double bond? And you could draw a second structure, maybe even a third structure that's equivalent to it. And really, again, what's really happening is those electrons are kind of bouncing around and can be at any of those locations at any given time. Any questions on that one? So once again here, this guy would have 2 central atoms in this particular case, which does happen. And again, we kind of want to keep the least electronegative still in that kind of main central position. And as I mentioned before, probably want to see too much double bonding happening here, because this bond here between the oxygen and the hydrogen is a polar bond, difference in electronegativity, with the oxygen being more negative, the hydrogen being more positive, and that is actually the hydrogen that pops off that makes it an acid when it releases the hydrogen, partly because of that polar bond that's there. It weakens the bond for the hydrogen to oxygen, allows it to sort of come off and act as an acid. Question? There are reasons that wouldn't happen. One of the reasons is that OH group is one of the things that makes it an acid. There's a whole group of acids which are known as oxyacids, and they all have that OH bond that allows that hydrogen to easily be released. And it wouldn't necessarily happen as easily if it was on the nitrogen. There's also something that you could use in terms of that type of question is we're going to talk about something that you could sort of calculate, for example, to help you choose between maybe I did want to put the hydrogen there, or maybe I want to have some other arrangement. And this was known as formal charge, which we'll talk about in just a bit here, but you can use that to help you decide between different structures and see which one's probably more favored than something else. So the short answer is that's sort of what makes it the acid part, and that OH bond is necessary for it to be an acid in this case. Yeah. Other questions? All right. So I drew some. Your turn just to draw like crazy. All right, let's do, why don't you draw SO2? Why don't you draw CO3 2 minus? Why don't you draw SH2? Why don't you draw HCN? Why don't you draw CO2? I'm gonna take a power nap here. NH2 minus. And we'll do lucky number N2. All right, we'll take some time here, lay up some nice Lewis structures there and see what you come up with. In case you need, here's some periodic table. It'll be helpful. Strain your neck looking to the right. So before we take a look at these, just to go back and answer the sort of the earlier question as well, which was in terms of the hydrogen, could we attach it to the center? So if we took that approach where we put our nitrogen in the center, which is still the least electronegative out of those bunches, and then we put our hydrogen there on the nitrogen, and we followed our sort of rules there to assign electrons, we would do our single bond to each of these, right? At that point, again, it would be 2, 4, 6, 8 electrons, which still gives us 16 more to go. And if we put it on the outside, 2, 4, 6, obviously not to the hydrogen, 8, 10, 12, 14, and 16 at this point, right? And now we would distribute all 24 of our electrons. Is everybody good at this point? The oxygen here is short, right? The oxygen only has 6 electrons. Everybody else is actually good. The other 2 oxygens have 8. The hydrogen has 2 like it wanted. So if we were going to try to fix it by making a double bond, we would have to bring electrons in to do that. And we would get rid of those electrons. And in this particular case, would the double bond fixed it? Not. We could even bring it in to make a triple bond. The other pair of electrons, it's not going to fix it, right? And the other problem, though, would be when we look at it, even if, you once said, well, maybe I just want to bring those in and get rid of the oxygen. No, don't get rid of oxygen. Maybe I want to make like a triple bond or something like that, right? Still doesn't fix it, right? So that's the problematic with that arrangement. It can't work pretty much in any way to get everybody to the completed octet, which is ultimately the goal of bonding, right? Is to get everybody to that noble gas configuration. There's no way to do that. And even if you did manage somehow to do it, how many bonds is nitrogen picking up as I keep double bonding and triple bonding? Way too many, yeah. So it's going to push nitrogen over what it should have. So in this situation, you wouldn't need anything like formal charge because you really couldn't draw a proper structure that would meet the octet rule and still have hydrogen good as well and have the right amount of electrons distributed. Other questions on that? You would always sort of be short at somebody along the way. All right, so with that being said, let's come back this way and we'll start with the SO2. So we have 6 for the sulfur. We have 2 times 6 for the oxygen. That's 12. That's 18 valence electrons. Once again, if we look at sulfur and oxygen, they're actually in the same group on the periodic table, like something like that. And we see that oxygen is further up, which means it should be more electronegative. And that means that the least electronegative atom, which is the sulfur, should actually be in the middle. So we should put the sulfur in the middle. We should put the oxygens on either side. And again, we're going to connect with one line that uses 4 electrons, 2 for each line. We got 14 to go. So once again, filling up our outsides, 2, 4, 6, 8, 10, and 12 at that point. So at this point, I have put on there 16 electrons. I still actually have 2 more electrons to go, and they should then go to the central atom as dots. And that's how the central atom should have dots on it, by the way, not double bonded up everywhere on each side. Yeah, so it actually should have those lone pair of electrons on the sulfur. At this point, though, we have now distributed all 18 of our electrons, and we could see, or hopefully we could see, oxygen's good, but we are running into a little problem here at sulfur, right? Sulfur has only got 2, 4, and 6. Each of the oxygens have 2, 4, 6, and 8, so it's good. So our sulfur is not good, but our oxygens are. So we do want to fix it by making a double bond now that we have distributed our 2 dots there on the central atom. So put back my line there. All right, so once again, we're going to make our double bond by taking a pair of electrons. In this case, doesn't matter which oxygen I do it from. It doesn't, they're both equivalent. So you could double bond up to the left. You could also double bond up to the right. So I'll take a pair of electrons from this side and bring it in. And when I do so, I will end up with a structure that looks like this. Again, with those dots still on the central atom is what it should look like. Now, the oxygen on the right has 8 electrons. The oxygen on the left has 8 electrons. And our sulfur has 2, 4, 6, and 8 electrons happening at that point. That is the proper structure there for SO2 or sulfur dioxide. We also, because we did have the option to either double bond on the left or double bond on the right, we could draw again a resonance structure for this, which is basically the opposite double bonding effect there. So instead of double bonding on the right, I would then double bond over here on the left. So once again, these are resonance structures of each other, and resonance structures are usually separated by that kind of 2-headed arrow heading in both directions. Any questions on that drawing there? All right, continuing on to CO3 minus. So we'll go with our CO3 minus. So we got 4 for the carbon. We have 3 times 6 for the oxygen. And as was the earlier question, that -2 does mean that it has gained 2 electrons. So we do need to add 2 electrons there to our total. And that's going to give us 18, 20, 24 valence electrons in this case. Once again, comparing carbon and oxygen, which is in the same row or period on the periodic table. Carbon's over here. We once again see oxygen's further to the right. That means carbon should be in the center because it is the least electronegative. And we should have some oxygens going on the outside. We're going to connect with 1 bond here each. I'll go up here and draw it a little bit higher. All right, so 1 bond each gives us 2, 4, 6 electrons. We are then going to distribute the rest on the outside. So 2, 4, 6, that's filled. 8, 10, 12, that is filled. 14, 16, and 18, that is filled at this point. That is 24 electrons. Is everybody good in this case? It is the carbon here that's short. The carbon only has 2, 4, 6 electrons to it, 2, 4, and 6. So once again here, all those oxygens are equivalent. So we could bring in the electrons from any of the oxygens to make a double bond. So again, I'm going to take a pair of electrons and bring it in to do so. And that will give me a double bonded carbon up on top. And usually if it is an ion and you're drawing a Lewis structure, some brackets, and the charge on the outside is usually how you would do it. You could draw another resonance structure where we double bond, say, to the right. And you could actually draw a third resonance structure where you double bond to the left there. So over here, put it in here. Double bond over here. So these are actually 3 resonance structures that you could draw for carbonate. Again, those double bonded electrons are kind of moving around and at any given time could be at any of those oxygens, kind of moving through back and forth. And again, you could draw any one of these as a Lewis structure. So if you're asked to draw the Lewis structure for carbonate, you could lay up any one of these three pictures would be sufficient. If you're asked to draw all the resonance structures, you should lay up all the pictures that are up there. Any questions on that one there? All right, continue on here. We have SH2. SH2, a little HCN, I think I had. Just copy them over, CO2. All right. All right, so starting with SHN, SH2. So we have sulfur, which is group number 6. We have 2 times 1, which is for our hydrogens. So that is 8 valence electrons. This should be pretty simple. We can't put hydrogen in the middle, so it's got to be sulfur in the middle. Hydrogen on the outsides. We're going to do a single bond to each. That is 4 electrons. We still have 4 more to go, and we cannot put any more on the outside hydrogens as they are done. So we will then go to the center, and they will go on as dots, which will give me 8 total valence electrons. Sulfur's got 8, and each of the hydrogens have 2. So it's all good the way that it looks like there. Any questions on that one? Rolling to HCN. We got 1 for the hydrogen, 4 for the carbon, and 5 there for the nitrogen. That is 10 valence electrons. In this case, we know hydrogen shouldn't be in the middle. And once again, looking at the periodic table, we see carbon to the left there of nitrogen, which means it's least electronegative. So it should be the carbon in the middle in this situation. Once again, we're just going to do what we normally have done. We're going to single bond, which uses 2 and 4 electrons. We have 6 more electrons to go. We cannot put any on the hydrogen on the left because it is full. So we'll still put it on the guy on the right. So that is 2, 4, and 6 in this case. That is a grand total of 10 electrons. Is everybody good in this case? The one that is not good is carbon, right? It's only got 4 electrons. So we're going to try to fix that by making a double bond. So we're going to take a pair of electrons and bring it in to do so. That would give us something that looks like this. Did that fix carbon? It did not. It made it a little bit better. We're now up to 6 for carbon. So at this point, there really is no other option for a double bond. So now we should move to a triple bond to try to fix it. Triple bond works the same way. You got to still take a pair of electrons and bring them in to make that triple bond. And that will get you HC, a little triple bond action going on there. And at this point, we still have maintained the 10 total electrons. Now the carbon in the middle has 8 electrons, 6 from the triple bond on one side and 2 for the single bond on the other. And the nitrogen still has 8 electrons, again, 6 from the triple bond and 2 from the lone pair there. Any questions on that one there? Yeah. If you had a different element, can you do 2 double bonds before? Yeah, so that's what I was saying before. And actually the next example might be a good one to answer your question. But if there is an option to perhaps make another double bond, you would want to try to do that and sort of exhaust all the double bonds before you move on to a triple bond. That usually will result in a much better Lewis structure in that case. Yeah. Other questions? So with that in mind, let's take a look at this one, which might be a good example of that. So we do have carbon here, which is 4. We have 2 times 6, which is oxygen, is 12. And that's 16 valence electrons. Once again, our oxygen further to the right than our carbon. So carbon should be in the middle. Oxygen on each side. A single bond to each. 2, 4 electrons. 12 more to go. So that is 2, 4, 6, 8, 10, and 12. So at this point here, what we see is our carbon is short. It has, again, just 4 electrons. The oxygen on the outside is good. They both have 8. So we can make a double bond here. And once again, we could double bond either side. So we'll make our double bond. And if we do that, we will end up with something that looks like this. And once again here, got better for carbon. We're now up to 6, but it did not fix carbon. So as to your question, at this point, you could lay up a triple bond, but the better move is we could still double bond the other side as well. So that is probably the better move in this case. And what you want to do is that, and we'll explain why in just a bit, why we probably wouldn't want to triple bond that up here. So we're going to bring those electrons in on the other side, and that will give us actually a double bond happening on both sides here of carbon dioxide. And again, at this point, that will now give the carbon in the middle 8 electrons, and each of the oxygens on the outside will have 8 from the double bond and the lone pairs that are there. Any questions on that one? So as I said, definitely try to exhaust your double bonds before moving to a triple bond. So again, we want to think of these things as sort of our last resort to sort of fix something. So we kind of want to run through, okay, single bond, did it do it? To 8, no. Okay, did double bonds get us fixed? 8, no. If not, then triple bond should be your last resort at that point. Otherwise, you probably drew it wrong, I would imagine. If you need there's no like quadruple bonds or 5 bonds or things like that. In a sense, there are actually, but we'll talk about some of those in this bit. All right, the last couple is NH2 minus and N2, I think, is what we got left. So we have NH2 minus and N2. So nitrogen here is 5. We have 2 times 1 for the hydrogen. And here we do have a -1, which means we do need to add 1 more. Otherwise, we're going to be a little bit short. That's going to be 8 electrons, I think. And in this case, once again, we do need to go nitrogen in the middle, hydrogen on the outsides, single bond gives us 4. We cannot put any more on those hydrogens. So again, as pairs of electrons, they will go to the central atom. Put a little bracket and a minus on it. And again, here the nitrogen has 8 electrons. Each hydrogen has 2. Any questions on that one there? And lastly, on our journey of Lewis structures here, we're at nitrogen, which is 2 times 5. That is 10. In this case, there is no central atom, so there's going to be side by side is the way to go on that. And even if there is no central atom, you can still follow the same rules that we've been doing. So we'll just connect these guys by a single bond, and that will give us 8 electrons to go. So we'll just choose 1 to put them on for now. So 2, 4, and 6. And then we have 2 more that will end up, say, over there on the guy on the left. Is both nitrogens good in this case? Is not. The guy on the left has only 4 electrons, so we can still follow the same procedure we did previously. We'll try to fix it by making a double bond. So we're going to bring that in, and that will get us a double bond here. Once again, that does help the situation. It gets the nitrogen on the left to 6 electrons, but it is still short of the 8 that it needs. So in this case, we will go for a triple bond. So we'll bring those pair in, and that will get us a triple bond between them. And now each of the nitrogens there will have 8 valence electrons. They're happy, which is why nitrogen in this case actually has a triple bond to allow, again, each of those guys to get to that noble gas configuration. Once again, that is the purpose of all this bonding, is for everybody to achieve that noble gas configuration in terms of electrons. Questions on how to properly draw Lewis structures. I'm going to imagine you need to know how to do that, I would assume, yes? Okay. All right, let's see here. So to answer perhaps a question that was asked as well and sort of answered, but to also help us understand why maybe we wouldn't, in the case, say, of something triple bond versus put on another double bond, we could actually look at what is referred to as formal charge. And formal charge in a Lewis structure is really the difference between the valence electrons in the free atom and the number of sort of bonds it has and non-bonding electrons that it has. So to calculate the formal charge And you could do this for any element that's, or atom there, or element that's in your Lewis structure. You take the number of valence electrons in the free atom, you subtract it from the number of non-bonding electrons. And those are like individual electrons, like how many there are individual dots basically on your Lewis structure around that atom, minus 1/2 the number of bonding electrons. And that will give you a formal charge. And we can use formal charge to help us. One of the things that we use formal charge really for is to help us choose, for example, between different Lewis structures as to which one might be a better Lewis structure versus another. As you know, you can kind of put things together in different ways. And we could go through each of the Lewis structures in each of the atoms that are there, and we could kind of calculate what the charge is and really sort of like what the charge distribution would be in that sort of bonding arrangement. And some of them is good and some of them is not so good. So we'll take a look at ozone. And if we drew ozone, it would end up something like this. And we could calculate the formal charge for each of the oxygens that are here. I'll just call this oxygen 1, oxygen 2, and I'll call this guy oxygen 3. So if we do oxygen 1, which sort of looks like this, we could calculate the formal charge by taking the number of valence electrons in oxygen, which is 6. We're going to subtract it from the number of non-bonding electrons there are, which in this case is 2 and 4 non-bonding electrons, minus 1/2 the number of bonding electrons, which each line is 2 electrons, so that is 2 and 4. So that gives me 6 minus 4, which is 2, minus 1/2 of 4, which is also 2. And that gives me a formal charge for this oxygen of 0, basically. Now, if we look at oxygen number 2 there, kind of looks like this. Sort of what it looks like. We could calculate the formal charge on this guy. And if we do that, the formal charge once again would be 6, because that's the number of valence electrons in oxygen, minus the number of non-bonding electrons in this arrangement, which is 2, minus 1/2 the number of bonding electrons, which is 2, 4, and 6 in that case, 2 for each line. That gives me 6 minus 2, which is 4, minus 1/2 of 6, which is 3. And that's going to give me a +1, I believe. And that oxygen in the middle in this arrangement is kind of carrying like a +1 sort of charge. Lastly here, if we look at the last oxygen, which looks like this on the right there, we would do our formal charge here of 6 minus the non-bonding electrons, 2, 4, and 6, minus 1/2 the number of bonding electrons, which would be 2. That's going to give me 6 minus 6 is 0, minus 1 basically, gives me a -1 formal charge on the guy on the outside. So in this particular arrangement, the oxygen on the right is carrying a more negative sort of charge. Guy in the middle has more of a positive charge. And by the way, when you calculate the formal charges, one of the things to know if it's a good structure or not is it should equal the overall charge. So that equals 0, right? So that is what the overall charge is here in this particular case. Any questions on that there? So why don't you try one here? Let's take a look at our carbonate that we drew earlier. Calculate the formal charge on each of those atoms and see what you come up with. We'll start with our carbon here, and our carbon has basically looks like this. So we got 4 for carbon, which is the number of valence electrons in carbon, minus 0 in this case, as there is no non-bonding electrons there around the carbon, no dots, minus 1/2 the number of bonding electrons, which would be 2, 4, 6, and 8. And that's going to give me basically 4 minus 4, which means 0. So in this structure here, our carbon is hanging out with a 0 formal charge. If we look at our double bonded oxygen, which looks like this, it is going to end up being 6. I guess I shouldn't use dots there, huh? We will end up with 6 minus our non-bonding electrons, which is 4, minus 1/2 our bonding, which is 2 and 4. And that gives us 6 minus 4, which is 2, minus 1/2 of 4, which is 2. And that's going to give us a 0 here for our double bonded oxygen. Going to our single bonded oxygen, we're going to have 6 minus our 2, 4, and 6 electrons, minus 1/2 the number of bonding electrons, which is 2. And that will give us 6 minus 6, which is 0, minus 1/2 of 2, which is 1, which is a -1. So we got a -1 here. And as you haven't guessed yet, that will also come out the same, since it's just the same, just like our double bonded oxygen came out the same as the previous one, the other one it has there. So in this particular case, our -2 charge is really hanging out at the single bonded oxygens. Is really where that -2 charge comes from. Because of the electron distribution in this case, that's actually where our charge comes from. Question on how to calculate formal charge. So as I mentioned, what we really use this for a lot of times is to help us decide, maybe between two different structures or several different structures. So the general guidelines for formal charge is this: if you could draw a Lewis structure where frankly you have no formal charge, everybody kind of zeroes out on the formal charge, that's kind of ideal. Yeah, so if you calculate the formal charge, you got zeros hanging out, or mostly zeros everywhere. That's probably going to be a better structure than one where you have obviously non-zero numbers. Lewis structures with really large formal charges like 2, 3s, 4s, whatever it may be, are probably not plausible. It's probably not the best structure to end up with. And lastly, if you're kind of choosing between two sort of Lewis structures that have sort of a similar distribution of formal charges, like maybe they both have -1 and +1s, you would want to choose the one where the negative formal charge ends up on the more electronegative atom, because again, the more electronegative atom should be drawing the electrons towards itself, which means probably in the better structure, it will have more of a negative sort of charge because of those electrons coming towards it. So again, if you sort of have two structures where you have +1 and -1, but like your -1's on the least electronegative in one, but the -1's on the more electronegative in the other, then the one where it's on the more electronegative would probably be the best sort of structure. And we'll look at some examples next time of using formal